Hi, this video is about solving example problems with acceleration. Let's start with a discussion about this idea of the change in, which we see represented with the delta symbol. The change in any value, regardless of if it's physics or not, is calculated by the difference between the final and the initial values. So for example, that Pokemon card that you bought a few years ago, today its value is probably $2. That's our final value. The initial value that you bought it at may have been $50. So to find the change in the value, you take the new value, the ending value today, and subtract the starting value, the initial value. That gives you a change of value of negative $48. My cat Pancake, he has gained some weight over the years. He's not a very big cat, but he weighs probably about 15 pounds now, whereas we got him at about 8 pounds. So to find his change in weight, we do the final value, 15, minus the initial value of 8, and that gives us a positive 7 pounds. So he's gained 7 pounds. This can be done with physics quantities as well, especially with velocity when it pertains to acceleration. Let's say you're backing up your car, you're in reverse, and you start out going 2 miles per hour backwards, and then you start going faster and faster backwards. So you start out in the negative direction, going negative 2 miles per hour. Just the negative here just means moving backwards. So you're moving backwards at negative 2 miles per hour, and then you start going faster and faster and faster backwards. You end up at a velocity of negative 10 miles per hour. So to find the change in your velocity, you do the final minus the initial. So negative 10 minus negative 2. Now when you're doing a subtraction and you're subtracting by a negative symbol, these two negative signs turn into a positive. And so you end up adding negative 10 plus 2, and that gives you a change in velocity of negative 8 miles per hour. So we can write this idea of final minus initial like this in physics. We use these little subscripts here, little letters below the regular letters. So the change in velocity is the final velocity minus the initial velocity. So if you look back at our acceleration equation, we can now rewrite that an additional way. So instead of writing acceleration as delta v over t, you could rewrite that as acceleration is the final velocity minus the initial velocity divided by the time. And this is one that we'll often use when we're doing word problems, and you'll see why. Let's look at one. So let's say you have a car that starts out at rest, and then it starts accelerating, speeding up uniformly, which just means at the same rate at all points. So it accelerates uniformly at 2 meters per second per second. How fast will it be going 1 second later, 5 seconds later, 8.5 seconds later? So we have 3 questions here. The first 2 are pretty straightforward because if you're accelerating at 2 meters per second, it actually is a lot easier to just make a little data table here where you put the time and velocity. At a time of 0, you were at rest. It said here it starts at rest, so you put a velocity of 0. And for every second that goes by, we add 2 meters per second each second. So 1 second goes by, we add 2 meters per second. 2 seconds, 4 meters per second. So each time we're going to add 2 meters per second each second. So as long as we're dealing with whole number seconds here, it's pretty easy to find a velocity at a later time. But what about if it's 8.5 seconds? I mean, we might be able to do that in our head too, but just in case there's a more complicated question in the future, I wanted to show you a way of using our equation in a way that makes it easy to find the answer here. So right here in red is our original acceleration equation, but with the new form written at the top, final velocity minus initial velocity. We're looking for the final velocity after 8.5 seconds, right? The initial velocity was 0. What's the final velocity after accelerating for 8.5 seconds? So we want to solve for VF. We want this final velocity to be but basically isolated by itself in the equation, so we can set it on one side of the equation and set everything else on the other side so we know what it's equal to. So to do that, we need to get it out of this fraction. We need to multiply it by t over here to undo this division. All right, by doing that, we cancel out the t's here, but we end up doing the same thing to the other side here, t times a. So we usually rewrite that with the time always coming at the end. So that's going to be acceleration times time equals vf minus vi. Now we're going to add initial velocity to both sides. Those will undo each other here. They'll just cancel out. And we're left with the initial velocity plus the acceleration times the time is equal to the final velocity. Now I've flipped that down here, and this is the more standard way of writing this equation. So this is another pretty common equation we use. This allows us to find the final speed after you've been accelerating. Sometimes you want to know how fast you're going after accelerating for a certain amount of time. So you do that by finding first your initial velocity and then adding on to that any acceleration that happens multiplied by how much time passed. So let's do that over here for the 8.5 seconds. The initial velocity was 0. We accelerate for 2 meters per second for 8.5 seconds. So multiply those together, you get 17 meters per second. Now, because we only have one significant figure here and we have 2 here, we can only have one significant figure for our final answer. So we need to round this, and since this is a 7, we will round up to 20. So the final velocity is 20 meters per second. Let's look at a couple more examples here. Let's say you have an apple that's rolling at 1.8 meters per second until it reaches a downward slope, and then it begins accelerating at 4.5 meters per second. How fast will it be going after accelerating for 6 seconds, 6.0 seconds? So I'm going to use the guess method here to help me kind of outline the things that I know, the puzzle pieces, and how to put them all together. So the pieces that we know is we have an initial velocity of 1.8 meters per second. I know that because that's how fast it was going before it started accelerating. So you have to translate in your mind from this word problem into physics quantities. Okay, the apple was going at 1.8 meters per second before it started accelerating. So that's going to be our initial value for the velocity. The acceleration is 4.5 meters per second. Time is 6 seconds. Our unknown quantity in this case is how fast it's going after the acceleration. So this is going to be a final velocity. So we're going to use that new equation we just saw. A final velocity is initial velocity plus acceleration times time. This time we have an initial velocity of 1.8 meters per second. We have acceleration and time substituted in. Multiply these together, you get 27 meters per second plus 1.8 meters per second. That gives us 28.8 meters per second. We need to round that to have two significant figures, so that's 29 meters per second. I've got one more challenge question for you here. I want you to think about it. A lizard moves at a constant speed of 1.44 meters per second for 7 seconds. What is its acceleration? I would encourage you to pause the video and try to work this out for yourself, so I'll give you a second to do that. If you really want to learn, it helps to think through it yourself first. All right. The trick to this question is that it says the lizard is moving at a constant speed. Well, if you're moving at a constant speed, that means your velocity is not changing. And so, therefore, if the velocity doesn't change, there is no acceleration. So the answer would be the acceleration is 0. So you might be tempted to try to work out some kind of problem with this, and that would make sense in many cases. But when you see the words constant speed, that's a clue that there is no acceleration here. So watch out for any kind of problems like that. So that's all I've got for you in this video. Remember, everything you have is a gift.